Swayam Prabha. Digital India. Educated India.
So this lecture is a little bit to tell about this proactive design and maintenance strategy, which is coming up as a. I'm not saying that it was not there, but only thing is that it is coming more and more into prominence in the industries, because now there are so many tools are available for corrosion monitoring, and using those tools, they can get information on how the place where the equipment is used and or structure is made. They can understand about the conditions there, and based on the condition, they can design the product. And while the product is working, again, they can use the sensor data to monitor what is happening. Even the paint, when they do the painting, big buildings, even that is monitored today. And then they can collect that data. Again, there are a lot of development in the computational power, so they can use these machine learning algorithms and things like that to analyze overall what is happening. They can make a lot of predictions from that. So wind turbine industry is so much make use of this. So this proactive design and maintenance strategy as a kind of a way of doing the things has improved over the last few years so much because of this availability of all these things. In this course, we are start from the starting, we were discussing about the corrosion, right? When you take the corrosion is an application-oriented field. So there is corrosion science and there is corrosion engineering. We discussed about the corrosion science, we discussed about a little bit of fundamentals of corrosion, about thermodynamics, kinetics, the electrochemical basis of it. With that as a basis, when you try to make the product that is, not protected or having less corrosion susceptibility and things like that, that's what we call the corrosion engineering. And the corrosion engineering, when it comes, one of the things is that we make the products which is having less corrosion, or we develop the corrosion preventive measures and control measures, and at the same time, it is also important to develop corrosion monitoring measures and how we can monitor when the structure is installed at different places. Monitoring alone is not enough. While monitoring, we also need to analyze the data. This data has to be used again back to the design. And so this is that brings together all these terms, what I'm talking about, this proactive design and maintenance strategy. And after your studies, if you are going to an engineering firm, and engineering firm is making products, when you are making a product that has to be corrosion resistant, and then you will be going through all these things there. It's a part of that. So when it comes to the PDMS, that is this proactive design and maintenance for corrosion control, things like this come. So the first thing is a proactive corrosion design itself. Like while designing the product itself, you make sure that it is that design is meant for reducing the corrosion problem. And in order to do that, you need to know you need to do the mission profiling. Mission profiling means you need to know that in the life cycle of the product and what kind of conditions it experience. If it is Chennai weather, what is the weather conditions here, and that weather conditions, how it changes over the period of time, just to get an average value. And this mission profiling is important. Unless until you get this mission profile, you cannot do the proactive corrosion design. You can understand that we were talking about the wind energy part, which I was presenting you as talking about this analysis, what we did with the corrosion coupons, with many wind turbines. Ultimately, the VESAs get that, although it's a limited amount, the information what VESAs get out of that is this one, like the mission profile of this area. And from that mission profile, using that, they can do the proactive corrosion design. And once you do the proactive corrosion design, and next stage is when the system is installed or going to be installed, and the corrosion monitoring and prediction. And so in order to do the corrosion monitoring, you need good corrosion sensors. Not only that you need corrosion sensors, but these corrosion sensors has to be also online, and so that you can collect large amount of data on a hourly basis or something. You can produce a large amount of data, and then that data can be used again back to these design aspects. And so there, the improvement in the this information technology and the computational power and all those things comes picture. Once you have these two together, and then also come to the point that the condition-based preventive strategies, and so that is little bit of part of this proactive corrosion design, and proactively introduce the preventive measures based on this mission profile and improve using the online monitoring. So sometimes what will happen is you don't get that much information in mission profiling. So you start with some preventive measures, but then you improve that preventive measures, and as you get more and more information from the online monitoring and the sensing data. And then it comes to the condition-based maintenance strategies. That means that since you have all these information, mission profiling, and also the online monitoring of the system, which also will allow you to plant maintenance or corrosion product, this monitoring, prediction, and control. Maybe there's control as well that is possible in that. As I mentioned that, when you have the wind turbine, the maintenance cost is very, very high and extremely costly. And that means that you need to planning and reducing the number of visits to the maintenance itself is save a lot of money. And that is possible with all these things. So that all together, that brings this PDMS, what we are talking about, is proactive design and maintenance control. So everything is interlinked as well. That's the way these companies work. But in order to do this, first things what you need to do is that the mission profiling. And that means that little bit we talked about yesterday, this climate data analysis and things like that. So you need to know the place where it is used and certain conditions and corrosion classes and things like that. So a little bit on elaborating on that, that is most of the time what we have is that atmospheric corrosion is the biggest problem, although there is corrosion in the full immersed conditions, but characteristically the full immersed condition corrosion is much more possible to predict compared to that of the atmospheric corrosion. Atmospheric corrosion occurs because of one of the key things related to atmospheric corrosion is the moisture in the air. Because whenever there is a moisture and air together, always some of the air molecules will be replaced with water molecules. So the total pressure in the air will be a combination of the partial pressure of the air and partial pressure of water. That's what you are going to have. That partial pressure of the water is also temperature dependent. It obeys the ideal gas law, where pressure is constant and you have a certain volume, and then it is temperature dependent. And so that way, depending on the temperature, you have different amount of water content in the air, and that's what we call it as humidity. And that is one of the key things that is determining this corrosion behavior, because depending on the temperature and humidity and certain conditions on the surface of the metal, which I'll come later, and then you can get the condensation, and this condensation is the one that is causing the corrosion. We express the humidity in terms of absolute humidity and relative humidity. Absolute humidity is the amount of moisture, total water content in the air. As we can see that, or as we expect, with increase in temperature, the air can hold more water. And so the absolute humidity changes with this temperature in the air. And so that's the total quantity of water. But for engineering applications, if you always say this absolute humidity level, it is very difficult for anybody to understand that is the humidity level for engineering applications, to get an idea about what is the condition in a place. So normally we use instead of absolute humidity, we use the relative humidity. Relative humidity is expressed as a relative value, where you have the saturated humidity level. At any temperature, you have a saturation humidity level. So which means that 100% humidity, we mean that you cannot put any more water into the air at that particular temperature. So in this case, if you look at it, this is the maximum level of water you can put into the air at 31 degrees centigrade, for example. So there's a maximum amount of moisture that you can put. So the relative humidity we express that if this is the actual humidity condition and this is the maximum level of absolute humidity you can have, this ratio, and that is what we call it as a relative humidity. So that is much more easy to understand. That means the 50% relative humidity means at that place there is 50% of the maximum water content that's possible. 50% of that is there in the air. That's what it means. But relative humidity also has a problem at the same time when you express. What is the problem with the relative humidity? So relative humidity, Chennai, we have a relative humidity of 70% now. If you take Copenhagen, also maybe having a relative humidity of 70% now. But what is the issue there? What you need to understand? It has both Copenhagen and Chennai is having the same relative humidity. But what is the issue? Since the temperature is different, absolute water content in the air in Chennai and Copenhagen is different. Copenhagen with 70% relative humidity, having a temperature of probably 15 degrees centigrade, have less water content in the absolute water content in the air compared to that of Chennai with 32 or 33 degrees centigrade having this 70% humidity. You have a higher water content. Like here, what is happening? So lower temperature has a lower water content and 30 degree, you have a higher water content. So absolute humidity, relative humidity will not tell you the absolute humidity level. Absolute humidity will not tell exactly like easy way to say express the this humidity level as 50% like relative humidity. So that means that whenever you are doing a modeling or something like that and you need to take into account the actual moisture content in the air, then you need to go for the absolute humidity rather than the relative humidity. But relative humidity is much more easy to understand for us, and that way it's much better. Related to this humidity level, there is the most important term is the dew point, because dew point is the one that is determining that when you get the condensation on the surface. So which means that there is a engineering diagram called Mollier diagram, and Mollier diagram shows the stability of water as a temperature. That's exactly what it shows. Some Mollier diagram also will have enthalpy part, but here it is shown only the temperature and water content in the air. And that shows that, for example, if you take temperature 30 degrees centigrade, 30 degrees centigrade if you take, and if the humidity level is 40% relative humidity level, and the water content in the air is 10 grams per kg of the air, like that. And on the other hand, if it is same temperature, 30 degrees centigrade, and if you go to the 90% humidity, this goes to almost 25 gram per kg of air. So it shows the amount of water that the air can hold as a function of temperature. That is a nice thing which this Mollier diagram shows. Mollier diagram also shows this curvature here. That curvature shows that at any humidity level, if the temperature drops below this value, so you can see that you are starting at 60 degrees, say 60, this is 20, so this is 60% humidity level. So you are starting at 60% humidity level, and you are cooling down the surface. When you cool down the surface to this one, automatically you increase the humidity to 70% humidity, because the reason is that you reduce the temperature. So the absolute water content in the air is equivalent to higher humidity level. As you cool down like that, you reach the saturation value here. Once you cross the saturation value, the air cannot hold any more water, right? So this curvature shows that at any humidity level and temperature, below this curvature, the humidity level is equal to 100%, and which means that the air cannot hold any more water, and the water will be released as a condensation. That is what we get the condensation. So whenever the humidity level is close to 100%, we get condensation. But at the same time, one of the important things which I'll show later, that you don't need 100% humidity to get the condensation on a surface, because from the temperature point of view, when you look at it, you need 100% humidity to get a condensation, but actually you don't need 100% humidity to get a condensation, because, no, the point I'm saying is that when you, as you cool down, see, when you take a beer can and you put it on the table, in the air you have 70% humidity. What is happening is that near to the surface of the beer can, because there is a cold air, that in that cold air, the relative humidity goes up because the temperature is dropped, and that, so near to that cold air you reach 100% humidity, and then you get the condensation. That's what is happening, not because of the 70% humidity here. The point I'm saying is that You don't need actually the 100% humidity level to get the condensation. You will see that later, because any surface is concerned, there is surface roughness, capillaries, and you also have other impurities which is sitting on the surface, which is hygroscopic, and all these mates, that is, you don't need actually 100% humidity level to get the condensation. That's a problematic thing actually for us, because you don't have to go to the saturation level to get the condensation. But dew point is a most important factor in this case, because that determines actually when you get the condensation. And that is the reason that now we can also understand that why we did the classification. There is a original classification of the climate called this Köppen-Geiger classification, which is there for a very long time. Many years back, they made that classification of the climate. But this classification of the climate is mostly done with the vegetation, agriculture, rain, and things like that, like the tropical, subtropical, and things like that. You will see that in this classification. And this tropical, subtropical, and everything is made based on the agriculture and rainfall and things like that. And that's the reason that we collected in another way. And now you can also understand that why we took the dew point temperature as one of the key things in this classification, because that is one of the most important things that determines the condensation factor. So with also comes to that most of this atmospheric corrosion is actually the thin layer corrosion. And when it comes to the thin layer corrosion, which we also mentioned earlier, that is, there are certain characteristics related to that, because thin layer electrolyte make it easy access for ocean and things like that. So if you look at the kind of a schematic representation of corrosion rate as a water film thickness, this is the effect what you see. If you have very low thickness, you have very low corrosion rate. Then you come to something like about this is 0.1 nanometer up to 1 micrometer. You can see the corrosion rate is steadily increasing suddenly, and then you reach after 1 micrometer, and then you start getting into the almost bulk regime, and you will see the corrosion rate is slowly decreasing. Actually, you see that there is a point at which you get a higher corrosion rate in the thin film compared to that of in the bulk. That's what you see in general. If you look at these three regimes here, these 1, 2, 3, 4 regimes here, and let us proactively look at what happens at regime 1. Why the corrosion rate is lower at regime 1? If you think thin layer electrolyte is sitting on the surface, and if you think that all the dynamics related to that, why the corrosion rate is lower when the thickness is really low? What could be the reason for that? Yes, less water, less conduction. That's what you told, right? So the ion transport is extremely difficult with that probably 10 angstrom of water film thickness means probably 1 or 2 molecular layers, and this is what you have with that thickness. Is extremely difficult for the ion transport, and that's the reason that although there is oxygen is freely available, ion transport is difficult, and that's the reason that you get a lower corrosion rate. Then as the thickness is increasing, the conductivity is increasing, and then you reach a point that the conductivity is no longer a limiting factor, and that means that since conductivity is no longer a limiting factor, you have a much higher ocean access because of lower thickness. That means a limiting current, what usually we experience because of the oxygen, will not happen. And then you get a higher corrosion rate. As the this thickness is increasing, you again get into the limiting current problem, and that way the corrosion rate becomes more like a bulk corrosion, things like that. So that's also the reason that interesting, because the thin film of water film is usually cause higher corrosion problem. Don't confuse this with yesterday's thin film we discussed in the electronics, because electronics this will not happen, because because of that? Huh? Yeah, leak current is there, but again, what will happen is if I do the water film thickness, usually we will not get a behavior like that. That's because we discussed about having a higher voltage on the PCB and water film thickness. No, you think about the cathode reaction. We don't have the oxygen as a cathode reaction because you have enough voltage for water splitting. So oxygen limitation is not there in that case. So this is what I'm talking about, normal corrosion, where the oxygen reduction is acting as the cathode reaction. So when you have a thin film, the oxygen access is higher, and so that is that's the reason that when you have an appreciable thickness of water film, because of that, the oxygen reduction reaction rate is increased, and that way you get a higher corrosion rate. Of course, this is, I also should say that this is a little bit theoretical. Again, it depends upon whether the substrate is oriented like this sometimes and substrate is oriented like this. The substrate is oriented like this, all the corrosion products form, it settles on the surface, and that add an extra barrier. On the other hand, if the sample is sitting like this, probably the corrosion product will not stick to the surface, and so that way the metal surface is always exposed, and then you get the behavior what we are talking about. So there are a few other factors depending on what corrosion product forms and things like that comes in. But if you are assuming that the metal is directly dissolving into the solution and you have a thin film of electrolyte, because the oxygen access, you get this behavior. So that's what here, just if you look at it, that is the corresponding equivalent circuit which we can represent for any corroding system. Simple equivalent circuit we can represent. You have the charge transfer parameters here, where you have the RP, that is the resistance polarization of the surface, and you have a capacitance because the double layer charging, so the double layer capacitance, and you have the this resistance polarization related to the charge transfer resistance, that is what is RP. And then addition to that, there is a parameter, this RS. So basically the water film thickness and this change in this what you see is a combination of how these RP and RS play a role together. So when you have the very low thickness value, RS is dominating, and so that makes this lower corrosion rate. As you increase this regime, RS and RP is working together, and then once you reach this one, RS is no longer a problem, and RP changes, reduces because of the higher oxygen access, and then what you see, this higher corrosion rate. So electrical equivalent, you can see that this is the way the things are happening, and that is also what you see here. So if you look at this studies which people have done at in the literature with platinum with a decreasing electrolyte thickness, so you can see that in general, with the decreasing electrolyte thickness, as you reduce the water film thickness, you can see that the oxygen reduction reaction is rate is increasing as we expect. And so here you can see that at the same time, how the resistance of the water film increases with the change in the electrolyte thickness. So you can see that the two parameters which are I mentioned, these RS and RP, how that is playing a role together with decreasing the water film thickness. One side, oxygen reduction reaction rate is increasing, and other side, resistance of the water film is also increasing, but it goes in the opposite direction with respect to the effect on the corrosion resistance. So that's also the reason that the water film thickness is important. Like yesterday, I have shown you, right, in the electronics, this one, why we are measuring the water film thickness. We are trying to understand that that water film thickness is not a continuous water film. We are trying to understand how this droplet structure is forming, and that morphology and things like that. So when you look at the water film formation on a surface, there are three parameters usually depends on that. One is the air humidity level, understandable. And with respect to the air humidity level, the temperature of the object related to this one, and that is determining the dew point. So at any temperature, if you know the temperature and if you the RH value in the atmosphere, you will be able to calculate the dew point. So that is the way we do. So sometimes basically what happens is that when you get I told you that yesterday we collect the climate data from all the weather stations located in the airport. That gives us only the temperature and humidity data. It will not give the dew point data. It will give the temperature and humidity data, but then we use this equation and corresponding profile for the dew point we create. So you can calculate the dew point if you know the RH. And so that is one thing that determines, so that we know that in order to reach this temperature dew point, in order to get this condensation. So that is the theoretical one, which needs 100% relative humidity level to get the condensation, but that never need 100% humidity level in order to reach the condensation if you take all these factors into consideration. So that means that any surface is concerned, metallic surfaces in general hydrophilic. because of surface charge and things like that, unless you have an oxide film, probably like aluminum oxide, which is non-conducting and things like that. Otherwise, the surface is hydrophilic, and that itself will make water film formation easy because water molecule get attracted to the surface. In addition to that, any surface if you take, there are kinks, and especially the size of this one is so smaller, and then you have the capillary forces. The capillary forces will make the water to get into the surface. So capillary will act as a hygroscopic surface, getting water absorbed so much. In addition to that, you can have the contamination sitting on the surface like salts, that's the reason that in atmospheric corrosion test site, they report how much chloride is deposited in a place. The importance of that one is this one, because the chloride deposition amount, it will tell you that also, that is what is the chances for condensation, because then you don't need 100% humidity level to get the condensation. So all these factors are also equally important because that reduces the level of humidity that is needed for the condensation to occur. So one is you need to have the dew point and temperature which very, very close. That's what is shown. There's a temperature effect, what you're talking about. And here you can see that in this case, Copenhagen climate in July, dew point temperature and this actual temperature is very, very close, but still it is not lower. Still it is, this dew point temperature is not above this. It is very close. You get lot of condensation on a car. That is basically because of the car surface is also having a contamination, which means that you don't need that 100% humidity level to get the condensation. That closeness is enough to get the condensation. That's the thing. That is because road salt and things like that deposit, and that is hygroscopic. Deliquescent property is a thermodynamic property which is there for all hygroscopic substances. Any hygroscopic substance you take, there is a stability. It is solid, stable as a solid and stable as in solution, and this is determined by again it is coming to the free energy part, and there is a particular humidity level this substance will start dissolving. So if you take sodium chloride will not dissolve into the water. If the humidity around sodium chloride is less than 75%, it will not. Thermodynamically, the solid is stable rather than in a liquid. Once this humidity reaches 75%, then the sodium chloride dissolved in solution is much more stable than the solid state. So it starts dissolving into the water, and that way it will become a sodium chloride solution. This is what we call it as deliquescence. And this deliquescent humidity level for different substances are different. Thermodynamically, we will not go into detail, but thermodynamically we can also see that when you mix two hygroscopic substances, so that means sodium chloride is having some certain relative humidity level. Now you take magnesium chloride is having another deliquescent humidity level. If you mix these two together, thermodynamically the combined deliquescent humidity level for the mixture usually drop. So that's much more dangerous. So that means that in the Europe, if they are using sodium chloride as a road salt to just melt the ice, then you have a relative humidity level, deliquescent humidity level of 75%. But on the other hand, if they are mixing that with calcium chloride and magnesium chloride to make the effectiveness more, this will be dropped further. Because thermodynamically, we can look at it in the books related to the deliquescent, this one, it shows that the mixture will have a deliquescence point which is lower than this. So deliquescence is one of the key things. Whenever we talk about deliquescence, we also need to talk about efflorescence, which is a crystallization humidity level. What it shows that is, if you take the sodium chloride, you keep increasing the humidity. So you have a sodium chloride here, and above that sodium chloride, you keep increasing the humidity level. When it becomes 75%, suddenly you will see that sodium chloride becomes a liquid. So it becomes a liquid. Then what will happen? Now you remove the humidity. You start removing the humidity. So you expect that it will come back and crystallize. It will not happen because of the molecular forces, the way the crystallization has to occur. Like, we used to tell about, in metallurgy also, you must have learned about when you do the casting, you need to do the undercooling, right? In order to get the enough energy for the nucleation and crystallization and things like that. Exactly the same thing. It will not crystallize here. Instead of that, you will follow this. It will crystallize at a lower humidity level with having an hysteresis. So this is what we call that crystallization relative humidity level. So it becomes water at this level, but it will become solid again only at 50% humidity level. That means that within this hysteresis area what you are talking about, it can keep the water, which is another problem. So once the deliquescence occurs, it will not crystallize back, even the humidity level is dropping below 70%. So both are important in keeping the water film. So yesterday I didn't mention this. So yesterday we were measuring the water film thickness. So I was showing that there's a clean surface with a certain water film thickness. Then we had this less hygroscopic adipic acid, which also provide us almost the same water film thickness. Now if you look at this profile here, you can see that the clean surface gives a profile like this. That means that this is the condensation, this is the evaporation, and when you look at the adipic acid less hygroscopic. Also, if you follow this profile, this black line, this green one, the black one is a clean one. You can see that again it exactly follows a clean one. So which means that hysteresis, this hysteresis what we are talking about for the adipic acid is almost not there. Adipic acid is immediately crystallizing back similar to that humidity level. The hysteresis is not there. So the crystallization humidity level is almost similar to the deliquescent humidity level for the adipic acid. But on the other hand, if you look at the glutaric acid, you can see that glutaric acid is not following that profile. So here it's not symmetric. If you look at this part, this is not symmetric, because you can see that in the case of glutaric acid, it takes a longer time for the moisture to be removed. So that means that you need to come down to higher, much lower humidity level in order to become dry. So if you take that as a time period at which glutaric acid is keeping the moisture, you can see that this keeps the moisture less time and this keeps moisture longer time. And that also increases the corrosion problem. So not just the deliquescent humidity level is important, but crystallization humidity level is important. That determine how long the systems can keep the moisture content, and that way the water film on the surface. So both are important parameters. So that's the reason that I just put only deliquescent humidity level here. But if you look at the literature, all kinds of ionic substance, there is a lot of work has been done determining the deliquescent humidity level and crystallization humidity level, because this is one of the key parameters everybody needs to understand, like how the water film is building up and atmospheric corrosion related issues and things like that. So this is inorganic substance, but similarly you will also see for the organic substance as well this deliquescence humidity level. So that means that all these, so chloride and all these depositions are important, but we cannot, when you come to the atmospheric corrosion side, we cannot take everything into consideration. Depending on the places, you can have so many different contaminations and which is coming to the surface. But at least we need to take certain things. That's the reason that there are few standards related to the contamination level, which is determine the place, aggressivity of the place. For example, from the chloride point of view, it is divided into this S0, S1, S2, S3, like that, because that shows that there is less chloride deposition to the high chloride deposition. So that means that this you can take it as probably inside the room, and this you can take it as an offshore, like that. So that shows that if S3 means, then we know that it is you need to expect that level of chloride deposition, and you can do certain calculations based on that. Similarly, SO2 content also made the standard like this P0, P1, P2, P3, like that, and that also shows a similar level of increase in the SO2 content. This is kind of a world level what you are talking about. So that means that all over the world, that's the kind of level at which you see, and that's the way it is divided. So that is one parameter. There can be more classification. There can be things also for H2S and like that, another table. I just put as an indication here. So you need to know the contamination level. That's one part. Second part is that you also need to know like how much the surface, there is a chance for the surface to wet. How can we quantify that? We mentioned that like 100% humidity level, the surface will, that means that 100% humidity means a saturated humidity level, surface will have water. Then we mentioned that it's not necessary to go to 100% humidity level, because if you have a deliquescent substance, you can get this condensation before. So taking chloride as the kind of common contamination which you see at most of the places, that's right? It's because seawater contains a lot of sodium chloride. Sodium chloride is one of the main contamination which you see on a surfaces which is causing the atmospheric corrosion. Taking that as a basis, deliquescent point of that sodium chloride is below 80. So that means that if your humidity level is higher than 80, there is a chance for water film formation on the surface of the material. Taking that as a basis, all the world climate has been divided into this time of wetness parameters, like a T1, T2, T3, like that. So TOW units are hours per year, which means that TOW T1 means 10 hours per year. There is a chance for having such kind of criteria. That's what it shows. Having a humidity level higher than 80%, and that means that there's a chance for condensation. You can clearly see that 10 hours per year is a very short time. It's an AC room. It's inside very highly protected room, and that's a place you can have such level of low this time of wetness. Then the time of wetness is divided between this one. When you go to this 5,500 hours of time of wetness, that is more like offshore, where you have a chance for condensation, this formation all the time. So time of wetness, which shows the propensity for condensation, that shows the contamination. There are more standard tables on that, and all these are useful parameters to determine and predict different things. Putting all these together, so we also want to put all these together there, right? Not theoretically. That's also the reason that people determine the corrosion class. So there is also a corrosion class division between the places, which is again determined along with the determining all these by using the coupons at different places, and that shows as a corrosion class, which is very, very important together with all these. So that is a corrosion class. Then we divide it into C1 to C5, and people also sometimes talk about CH class, which is totally offshore. And so this is the corrosion rate, and then they determine the corrosion rate for main structural materials, and that's a very good indication of predicting that. Like if the Vestas is making a wind turbine, placing at one place, and how much steel corrosion they can expect and things like that, do a lot of predictions from this. Just available data in the literature. You don't need to go into the mission profiling in that place, or they don't have to depend on the product installation sensor data. Yes. Yeah, that is, I just try to combine T3, P1, and that one. That is what is result in the C4. So it is just to show that that is equivalent to C4. Those combinations. Yeah, more or less. It's not like this is derived from that, but more or less showing that the C4 class, you expect such kind of conditions. That's all. Approximately. So what it means this? So this is the corrosion rate in gram per meter square per year. So which will not make much sense for us since it's gram. So if you take C4, that conditions, what it means is that it is about 1 micrometer per year. That is what you expect the corrosion rate in the case of around C4. That is, you can convert that, right? So that's what we expect. So this is also a reason that people have made the corrosive map as well at different places, especially the this seaside region, and showing that what is the corrosion level. There is corrosion map for Japan, China, US, and because this corrosion map is very useful for all these companies again to use for developing the preventive measures and the proactive design. There is saline concentration and the gaseous conditions maps, showing that what will be the saline concentration at different places. There is gaseous condition related SO2 things, there are maps. So there are so much, it is just to show you that there are so much information available in the literature already, that is, it can be used for a lot of prediction and advantages to do the proactive design. This is a type of atmospheric corrosion sites you will see at different places where you have these coupons which is exposed. Usually they expose at 45-degree angle to be same with everybody using it, because whenever you have an horizontal one, there is a problem because of corrosion product, whatever is formed, it will be stick or the deposition will stick. But this has, there's a chance that like in normal condition it flow off. So that's the reason that it put at 75%, 45 degree. this one, along with that, they will have corrosivity sensor sometime. They'll have time of wetness sensor, temperature and humidity sensor, chloride, and all these will be there along with that, so that they can get all this information from this one, from this test site. That is what I showed this table, although this is small. Like this is the kind of corrosion, atmospheric corrosion test site in Europe, which gives the data: corrosion of steel, corrosion of zinc, copper, aluminium, temperature, rainfall data, relative humidity, time of wetness, SO2 content, and chloride. Big information, right, for any type of prediction. And this is also color coded, like you can see that depending on this one, there's a color code, whether it is C1 class, C2 class, and things like that. And similarly, time of wetness, T1, T2, T3, P1, P2, based on that other, I think it is SO2 and chloride class as well. So just keep that in mind, and let us look a little bit more into the use of materials and design. And it's not that complicated, but it's less complicated, but it's important to understand. That is how you select the material, how you tailor the materials for better corrosion resistance. And although in all cases that's not possible. In corrosion engineering, that is certain, like, people to know about what material can be used in general, and with the corrosion understanding. That is basically we normally we say that all passivating metals are good for the oxidizing conditions, right? All passivating metals are good for the oxidizing conditions, because passive metals always form oxide film when you raise the potential, and oxidizing environment means it is automatically raising the potential, which means that in general we can say that all oxidizing passivating materials are good for the oxidizing conditions. Like nitric acid, hot oxidizing conditions like sulfuric acid, stainless steel, titanium, all these materials are useful because those are passive metals, and which forms the very stable passive film in the oxidizing conditions. So that's a general rule, thumb rule. We say that oxidizing passive metals are good for the oxidizing environment, and noble metals are good for the reducing conditions. And alkaline, then you can think about the Porbet diagram. So for example, alkaline condition, nickel is useful because nickel is very stable in the alkaline conditions. So this is a way also goes the thinking for material selection. There are hydrochloric acid warm conditions, which is very, very nasty conditions. There are materials, again, people made called Hastelloy, which is nickel, chromium, molybdenum, which is that's the only material that can be resistant into this hydrochloric acid, such conditions. And so people, those who are making, this corrosion flow loop for the oil and gas conditions, where in the oil and gas condition they do a lot of acidification. So once the oil well is made, now the reservoir is they need to fracture the reservoir. In order to fracture the reservoir, they need to put the acid into this one, hydrochloric acid. So because of that, there is a lot of testing of the material has to be done in this hydrochloric acid condition. So in order to do that, they need to make a corrosion flow loop, test systems. And a corrosion flow loop, then they have to make it with such costly materials. This will cost more than gold. And so they have to make it with such material, because otherwise the flow loop itself will corrode while doing the corrosion testing. Similarly, for the reducing conditions, normally we use the noble metal. And because it's reducing, it's already noble metal. So there is no, if you use the oxidizing metal, passive metals in a reducing condition, you're automatically dropping, right? All the passive layer is removed. So at least the better things there is the noble metal. So they use the noble metals for copper. So if you go to brewery, beer, they are making, you will see that big copper vessels, because that's the best conditions, best material they can use, because beer production, if you look at, that's the reducing conditions. And so that copper is the best material to be used there. So that is kind of a thumb rule. But if you look at, again, which we this we also discussed in the class earlier, if you look at the stainless steel, so what I did here is the Porbet diagram for iron, Porbet diagram for nickel, and Porbet diagram of molybdenum put together. Which earlier, in the afternoon, we were discussing, we were telling this, that is, if you put iron as corrosion region at many places, when you put chromium oxide is stable in this region, this part, but chromium is still not good in the acid conditions, lower pH conditions. Molybdenum has a oxide layer formation in throughout the pH, and then to increase the corrosion resistance in the alkaline conditions, they added nickel. So you can see that when you overlap this 4-by diagram, when you put all these layers together, that is how each of these alloy is tailorly added, and that way it is increasing the corrosion resistance, acid resistance, alkaline resistance, and repassivation behavior with the chromium and things like that. That also brings to a little bit more to tell about the stainless steel tree. That is, if you take the stainless steel tree, there are so many different types of stainless steel, which some of them are made for the to get a better mechanical property, but some of them are also made for getting better corrosion properties. There is variety type, austenity type, martensity type, and all of them are not having the similar corrosion behavior. And but it is also made for that purpose. Like martensitic stainless steel, nobody will use. No, it's not correct to say nobody will use for the corrosion work, but we know that that will have a higher corrosion problem. For the example, the oil and gas condition, all the tubing which is made, which is not stainless steel, but that's carbon steel, they use it in the martensitic structure, although they know that it has a higher corrosion compared to ferrite pearlite structure, basically because it has a higher mechanical property. So the mechanical property is giving the dominance there, and because of that they use this one, although it increases the corrosion problem. So, but there are some material in the steel, if you take the tailored for the corrosion resistance, there are many things you can look at it. So the stainless steel tree, each of these you can divide into branches, and you can really, it is a very nice idea that when you have the time to look each of these and why different alloying elements are added and what kind of corrosion property it improves and things like that. But I'm not going to take everything, but you can see that the Dev.Lce stainless steel here with this increased molybdenum content and nitrogen content, which gives a better corrosion resistance. So that's the reason that Dev.Lce is extremely good for higher corrosive conditions, and that is because of the higher molybdenum content. And here it is written that decreased nickel content for better resistance to stress corrosion cracking and higher strength level. And if you look at now another area here you can see that there is with the chromium and higher molybdenum content, there are many steels again developed for higher corrosion resistance. Corrosion stainless steel is built only for the welding purpose, because welding, when you have the welding, what's the biggest problem with the stainless steel when you do the welding? Sensitization, right? Because you form the chromium carbide, because of the heat treatment in the weld region, the chromium carbide will form at the grain boundary, and then you get intergranular corrosion problem. So in order to block that, if these alloys have titanium and niobium will make the carbon not to get into the grain boundary. Instead of that, titanium carbide and niobium carbide will be forming inside the matrix, and that way it will block the formation of the sensitization. So that those alloys are with this kind of additions is specifically made for the welding. So I just put a few of the things here for you to understand how they tailor the stainless steel. But I think when you have time, it will be very nice if you look at this kind of diagrams are available in the it's available in the literature. Now the engineering application, again it is important that is to look at the isocorrosion diagram, because these isocorrosion diagrams are created for, again, with the purpose of making it is easy for the industries to see that what kind of material can be used for different application. They created these isocorrosion diagrams. There are many isocorrosion diagrams. I just put here two of them. One is for the sulfuric acid and one is for the nitric acid. It simply shows it's an experimental diagram. You can see that the way the curves are going up and down, you can see that it is it's a corrosion is an experimental science. It's very difficult to predict anything with a theoretical sense. And so this is fully an experimental diagram, but what it shows that is that any line if you take here, that line is corresponds to a corrosion of isocorrosion of 0.1 millimeter per year. So as long as any line if you take this parameter, these two parameters of the temperature and sulfuric acid, if that you can keep below this line, you can expect that the corrosion level of that material will not go beyond 0.1 millimeter per year. So that's condition for this isocorrosion diagram. So if you take this 90L here, what it means is that, so if I take 40 degrees centigrade, I can use this material to a maximum of 60% H2SO4. If I go to 80% H2, I am above this line, I should expect more corrosion rate. So all those lines are correspond to 0.1 millimeter per year, and such kind of diagrams are so much useful for these industries. Again, if you look at here, I was telling in the discussion in the afternoon the other day, again if you look at here, you learn a lot of materials, this material tailoring the material for corrosion, like some of these alloys are with molybdenum, increase in molybdenum. So you will see that with increase in molybdenum, you can raise this level because the acid resistance of the molybdenum is increasing. And all these effects you will see if you compare these diagrams, and if you just look at each of them, look at the in the Google, you just look at the composition of that alloy, understand that how the molybdenum content has changed in some of these alloys, and then look at the curve, and you learn that really how this molybdenum is affecting. So this isocorrosion diagram is another thing which help the industries to do this. The other one is which Lakshman was also telling earlier, that is I'll come to the per number, but this is a critical, another important factor is when you use the higher temperature is the critical pitting temperature and crevice temperature. When you are using at a particular electrochemical conditions, there is a maximum temperature at which you can go, which make the material to resistance to pitting or crevice formation. Again, you can see that that changes with the material. And if you look at the different types of stainless steels, again that is tailored for this. Just if you look at here, you can see how the molybdenum content is increasing the temperature. So increase in the molybdenum content here in the stainless steel, you can also see that the critical pitting temperature is increased. Then again, what we are talking about, the acid resistance increase with the molybdenum, the tailoring and all those things you can see exactly in this diagram. Not only that, such kind of alloys are developed because they want to increase they want to use it at higher temperature. So these alloys have developed basically because the technology here, the engineering application, they asked for such kind of materials. That's the reason. Like the super alloys. Super alloy is developed because the aircraft industry wants to increase the temperature of operation of the wind turbine, not wind turbine, the engine of the aircraft at higher temperatures. Just for that purpose, people are trying to try to see that which material can withstand, and that's the way the super alloys have developed. Then the super alloys have entered into many other areas, but specifically that was developed because of the aerospace industry. Then connected to that, people also have developed, which Lakshman mentioned about that. Maybe I'm just showing here is a little bit more expanded form, because I think Lakshman was showing this one with the chromium, molybdenum and nitrogen. Per number, that is pitting resistance equivalent number, is fully empirical. Again, they did a lot of model alloys of stainless steel have developed, and from that they calculated that is how the composition of the steel is influencing the pitting resistance, and they formulated this equation. And earlier the first equation was this chromium, molybdenum with nitrogen. Now they also expanded that with chromium, moly is added, tungsten, there is a little bit of tungsten in the steel sometimes, that is added, nitrogen, and these are the impurities in the steel which we don't want. That's why it comes with a minus sign, and that is also added. So just I made a statement here corresponds to this equation. Like you can see that 0.1% sulfur has to be compensated with 12.3% chromium or 3.7% molybdenum. So on the other hand, you show that always we see that sulfur content in the steel is a problem because of manganese sulfide inclusion, formation and things like that. So how sensitive that formates the sulfur to the pitting, you can see that if because of this coefficient here, this coefficient is very high compared to that of the other coefficients. Slight increase in the sulfur content, you need to compensate that with a much higher amount of chromium and molybdenum. But all these are very, very nice things which corrosion engineering work, like academics and in the company which they have done and creating such kind of formulas which help the companies to design different alloys. Now coming to the design, there are also, it's nothing big in this, but it's important to look at it. There is also, we call it as a better design for corrosion protection, basically from the galvanic corrosion point of view, and also from the crevice corrosion point of view. So you can see that in each of these, you can see that that is preferred design that's to be avoided. You can easily understand, right, why. Such kind of designs will have whenever you have a acid rain or something like that, or rainwater itself, it's just collected here. You create a stagnant solution. In this case, there is a much more chance for crevice compared to that of here. Here, everything will flow off. It's the same thing here. You don't have a hole, and in this case, you have a hole, and that means that all the water, whatever is coming, it is gone off. So that's a better design, or this is a better design, like that, right? And so it's a very, so here you can see that this is preferred because this part is coming inside, and outside part is, there's a flow like this. But in this case, you can have the solutions which is coming and stagnant here, and that is not good like that. So all these arrangements you take, it is simple design things, but it matters a lot from the corrosion point of view, because otherwise you will create the crevice corrosion. This is mainly connected to the crevice corrosion, but it can also be, if you think about you are coupling two materials together. We discussed about, like a copper bolt on steel part is okay. On the other hand, the steel bolt on copper part is not good because of the anode cathode area ratio, and all these things are also come into picture. Just to show you that another integrated design, which we were talking about the sacrificial anode, things which, right, you are very familiar with, because the zinc coated objects are seen everywhere, which is the principle of having a cathodic protection, right, using a sacrificial material for the steels. Just to give you another example of little bit more thinner structures, and again this problem, like these automotive heat exchangers, and automotive heat exchangers use aluminum tubes. Here I have shown some aluminum tubes. These are big aluminum tubes. These kind of big aluminum tubes are used for HVAC applications, like the air conditioning, for that. But automotive heat exchange, if you take many of the tubes in the automotive heat exchangers are very, very small, because they want to reduce the weight. So automotive people are trying to reduce the weight even by grams. And that's the thing. So heat exchanger also, they try to tell the heat exchanger manufacturers that now your heat exchangers weigh 25 kg. Can you reduce that 23 kg? It's nothing big, but 23 kg like that. So what they try to do is that always they try to reduce this wall thickness of the tube. And that way they can reduce the material. So they make the better materials from the mechanical property point of view, so that they can reduce the wall thickness. And the wall thickness today is maybe around 200 micrometer. 200 micrometer is the wall thickness of the tube that is used as a heat exchanger tubes in the automotive industry. Now the automotive industry is asking that whether that can be reduced to 100 to 150 micrometer. So when you have a 100 to 150 micrometer thick tube, what's the problem? So this is a heat exchanger tube, and through that the coolant is passed. And they don't worry about the corrosion inside this tube, because the coolant is always with corrosion inhibitors and things like that, unless until you add water, but otherwise it is corrosion inhibitors and things like that. You don't worry about the corrosion inside. The only problem is corrosion occurring outside, and I think that if corrosion is occurring outside, it's aluminum is susceptible to pitting. One, that pitting is coming and going down. It needs only 100 micrometer to go down, so that you get a perforation. One perforation in one of the tubes, the whole heat exchanger has gone. So in this case, again, what they do is they just use a very, very thin layer of, so this is made of 3000 series alloys. They take the 7000 series alloys, which is aluminum zinc, which has a electrochemical potential more anodic than this one. So when they make the tube, they do the co-extrusion and make this tube. So this is 100 micrometer thick, probably, or if it is, say, 150 is the target. So this is 100 micrometer thick, means this layer will be around 30 to 35 micrometer thick. Just 35 micrometer thick layer, they put, that's what is shown here. So that the idea is that whenever there is a corrosion on the surface, it will go like this. In the case of zinc layers, it will not penetrate down in this case. as a protective measure for the heat exchanger tube, so that they can make thinner and thinner tubes, but at the same time, they don't need to worry about this pit penetrating through the wall thickness, for example. There is a lot of other things going on in the heat exchanger industry, because heat exchanger industry, another thing is that how we can increase the heat transfer. So for that, now people are trying to put this kind of pattern inside the tube. So when you have this kind of pattern inside the tube, the contact area between the water and the tube can be increased, and that can increase the heat transfer. But now we can see that when you put that pattern, from the metallurgical point of view, you are introducing a lot of residual stress, and that residual stress will cause corrosion problem. So this is another research area which is going on in the heat exchanger, how we can make the internally patterned tubes for the better heat transfer, at the same time reduce the corrosion problem. Other part now comes to that one is that corrosion monitoring by sensors. So there are so many, so you can, I also put a kind of a statistic that number of publications which is there in the literature over the years on sensor related things. So you can understand the interest of the sensor, like how much is there in the corrosion monitoring. But the most important this part is that you need, today is that you need the sensing part. Earlier people were looking mostly for a sensing part without many of this thing, but now also what they want is that you're having a online transfer, data acquisition and data processing and online transfer of data. And this is what people are looking for, and that's the way the different systems are coming up. So there are many corrosion monitoring systems. Our old one, the crude one, is the coupons which you have seen. But then people have developed with the galvanic corrosion sensors that are available, where they put multiple metals like this stacking, and then these metals are connected together, and when the corrosion is occurring on the top, these metals are coupled together, and that coupling will create an electrochemical signal, and from that they can determine that how much corrosion is occurring and things like that. So that is galvanic coupling one. There are EIS sensors, which we also have a sensor. I didn't put that here. We also have a sensor which we made, that is EIS sensor. Basically, we have some pattern like this, like these comb patterns which you are seeing yesterday, and which measure the impedance along with the temperature and humidity. Then electrochemical noise sensors, which almost like you must be familiar with the zero resistance ammetry type of technique, where you have similar two electrodes. So that means that the potential between these two electrodes should be zero. There is no current as well, but with the time, because that then you get electrochemical noise because of what is happening on one of the surfaces, and that is what here. ER sensor, this is among this is one of the sensor which is so much used. This electrical resistance sensors, because of its easy to use, that one. This electrical resistance sensor is simple as this. This is a steel wire, you think, the total steel wire. There is a two part of the steel wire. This part is covered by a coating, and this part is open. So this part is not important for us for the time being. Basically, in the electrical resistance sensor, what happens is that they keep measuring the electrical resistance of this wire. Electrical resistance of the wire depends upon the thickness, right, of wire. As the corrosion occurs, the thickness of the wire will be reduced, or the pattern will be reduced, and that will increase the resistance. So change in the resistance they can measure with time of this, and that can be converted into corrosion rate. It's a very, very nice sensor, and it's quite nice, easily you can measure it. Why we need this part is, which is put under the coating, is that resistance is also temperature dependent, right? Resistance of the metal is temperature dependent. So you need to have a temperature compensation. So if you take this one and calibrate by using that value, this one you can make the temperature compensation. Because this will not affected by the corrosion, this will be affected only by the temperature. So this is for the temperature compensation, and then you can measure the corrosion. It's so much used in the oil and gas industry, wind turbine, and everywhere. So this electrical resistance sensor is one of the things which is used so much at different places. Now it is also available in the miniaturized form, so it's much more easy to use. So I put this list to show that there are so many different sensors that are available, and more sensors people are trying to make. And there is a lot of things going on this side as well, like data acquisition and data processing side as well. And so it is a big thing that is today in this corrosion monitoring world, like in the wind turbines, which I mentioned, which I also showed this, why we are doing this and why that is important. So that's the last one. So just to give you a glimpse of, right, you must have got an idea about like why we do this, right? That is why we do this. The whole PDMS strategy is that the proactive corrosion and design, corrosion monitoring and prediction, condition-based preventive measures, and condition-based maintenance strategies. But all these are linked as well, as we are seeing, one to another. Yes, that's all this part.